Okay, so good afternoon. After 4 days of many talks, posters, and discussions, it's very difficult to pay attention to yet another talk. But still, I'm very confident to be able to pique your curiosity with the results I'm going to show regarding a very new and exciting field, application field for DA, meaning weather prediction for autonomous driving. So this is a work I have performed in the DWD with the strong collaboration of Soy Pasalidi, Christian Belsbaha, and Roland Pothast. Okay, so as I mentioned, our main motivation is autonomous driving. So currently, there is a strong interest in developing the technology necessary to allow a car to drive itself without the intervention of humans. And for that, it's very important that cars are able to sense the environment, understand it properly, and according to that, take actions. For that, it's very important, a key factor there is, of course, the weather. Both in the present state and also in the future, in the near future. And that becomes very clear when we think of, for example, driving under wet conditions, or with low visibility, or with snow, or even with a combination of all of them. So in this state of affairs, DWD and Audi, the car manufacturer, are currently running a collaboration project called FlowCard, where the aim is to use some new technologies like Internet of the Things and cloud computing, and also some more traditional ones like nowcasting and weather prediction, to produce a real-time weather forecasting with a forecast, with an updating cycle of the order of minutes. We want to do that in an affordable way, so we don't have a decayed computer, so we have to do it in a cheaper way to be able to do it operationally also. And that's why we are coming up with some ideas to be able to afford this, to perform this very fast forecasting, and still in a simplified way, but still producing good results. Okay, let's go into the talk. So after the motivation, I'm going to speak first about the new kind of observations we want to assimilate within the project. Afterwards, I will explain quickly which kind of algorithm we are going to use to assimilate these observations, and to produce this very fast forecasting. And then I will show some results we performed already with our prediction system, our original prediction system in DWD, and finally some conclusions and perspectives. Okay, so first of all, let's have a look at the observations we are trying to simulate. So within FlowCard, Audi is developing some prototypes of cars where many variables are measured. For example, you have traditional observations like air temperature, humidity, pressure, geoposition also, velocity, many other things, and also some more difficult ones, for example, visibility. That's something that we cannot really model right now that well. These cars are already connected. They are connected via 5G technology, and this information is being collected in a cloud, there processed, and later sent to DWD. So here we can see this is an app we have already to get all this information online. And we can see all the cars. We have not many cars now, but in the future this is going to grow, and eventually it's going to get really big. All these crowdsourcing projects are, of course, really promising because this is the thing that is coming. Okay, on the other hand, we have also road weather stations. So these are weather stations, as its name says, which are placed near the roads, and they have very high quality sensors measuring very different variables, for example, temperature, dew point, precipitation, and many other things. And they are very well calibrated, but of course they are beside the road. So this is not a normal meteorological station. We have to take into consideration that the road is changing the conditions. And in particular, for Germany, there is a very good coverage. For example, for Bavaria, we can see that we have more than 200 stations, and the time resolution is very high. We are speaking of seconds and minutes. Actually, you have too much information there. Okay, so this is the kind of the observation we want to assimilate. And as I said, the idea is to do it in the order of minutes, 5 minutes. That's our target. So how are we going to do that? We are going to use the idea of preemptive forecasting. But for that, I'm going to quickly show how the traditional analysis cycle for a filter works. So normally, we'll take an analysis. We will propagate it with the model to get a forecast. Then we will perform an ensemble transformation. Here I'm speaking of the transformation of the whole ensemble, not the anomalies, but the whole ensemble. And then, with this new analysis, we will start a new forecast step. Okay. For the preemptive forecasting, instead of stopping the model and doing this transformation, we just continue a bit. So we propagate forward. And then we use the transformation that was produced here. Okay. This idea was initially proposed by Etherton in 2007. He tested it in a barotropic vorticity model. Afterwards, in 2015, Madaus and Hakim used it for a realistic numerical weather prediction problem. And very recently, Podhas and Belsbaha formalized it mathematically and extended also for the smoothing problem. This ultra-rapid algorithm has some very interesting properties. For example, provided that the model and the observation operator are linear, we can show that they are equivalent. So instead of, we can produce here this new forecast based on another forecast and this transformation instead of doing it by evolving the analysis. So that's why it's called preemptive forecasting. We can also do it for different batches of observations, just composing different transformations for each batch. Something very interesting is that we don't need to reinitialize the model. And that's going to have very important consequences, as we will see soon. And because of that, because of this, we can just pick the variables we want. Because we don't need to reinitialize the model, we don't need the whole state. So we can just say, okay, we want to update temperature or the variables we want, and for the grid points we want also. And that's the point where we are going to save computational time. Okay, so how did we implement that in our system? Our system is the so-called KENDA system, standing for kilometer scale ensemble data assimilation system, which consists of COSMO-D2, that is a convection permitting numerical weather prediction model with a resolution of 2.2 kilometers. That's regarding the model. Regarding data simulation, we have a normal, traditional implementation of the LTKF following Hunt et al. 2007. We have a rapid cycle of 1 hour with 40 members and 1 deterministic run. And we have a set of normal measures to make the filter work, like inflation and localization, of course. And okay, so that's what we call the RUC layer, meaning a rapid update cycle layer. And on top of that, we want to create an ultra-rapid data simulation layer, where, as I said, we are going to produce forecasts with an update rate of 5 minutes, 10 minutes, 15 minutes, of that order. We already did it, and so we have already talking about the first experiment we performed already regarding this ultra-rapid data simulation was the following. So we perform a normal assimilation cycle with our RUC system. Afterwards, we produce a free run, just starting from this point. So this is continuous, all this trajectory. And then we use this transformation here, produced by LTKF, on the free run for different lead times. And with that, we produce the so-called URDA run. We use 3 kinds of observations, traditional ones, synoptic stations, radio zones, and aircraft. And here we can see some results we had for May in our system. So for lead time 0, both methods are completely equivalent. So these are the differences regarding the free forecast for the ground, from the ground layer in terms of pressure. So we can see they are completely equal. But now for a lead time of 5 minutes, we can see big differences. In the case of the traditional filtering solution, we have imbalance, which is, of course, well known. We introduce imbalance in the solution, while our URDA forecast doesn't have anything like that. It's quite stable. Now, if we continue increasing the lead time, we see that this imbalance starts spreading like in the form of waves. These are the so-called spinup waves. So these are, here we can see them very, very vividly. While for our URDA forecast, this is not taking place at all. We have a very stable behavior. This is the well-known spinal effect that takes place also in other variables. For example, for the case of temperature here, we can see also stable behavior, while a very strong spin-up here in the north of Germany takes place. So the result of that is quite clear. Of course, we know that because of this reinitialization of the model, we introduce imbalance, and the solution then, of course, is going to oscillate very widely. Of course, that depends on the variable. And for a while, for a particular spin-up period, so in German here, sorry, while our free run is not doing that, and of course, the URDA run is also not doing that. And so our initial hypothesis was that given this lack of spin-up effect for our URDA run, it should be somehow better than the RUK run for short lead times. And that we already verified. For example, for the case of this a case where we assimilated only pressure. This is temperature, wind, and pressure. Here there's no improvement, of course, because we are assimilated only pressure. But for pressure, interestingly, URDA is always outperforming our traditional method, our RUK forecast. For the whole lead time. So interestingly, for the whole hour, URDA is producing a much better pressure field. Now, if we assimilate more observations, for example, pressure, temperature, and wind, we see a similar behavior, but now for different variables. For example, for wind, both winds are improved, and URDA, again, outperforms RUK. Here, it gets a bit more difficult. Here, URDA outperforms RUK here, but not here. And temperature is always very complicated. There are many cross-correlations that are really messing up, and temperature is always not presenting a very strong signal. Well, so those were our experiments, which tell us that our URDA approach appears to be very promising for our purposes, meaning that for short lead times, we can have a high-quality forecast, but at a reduced computational cost that we will be able to afford in our computational center and to do it, in order to do it operationally. Something that we got for free was this lack of no spin-up. So we were just planning to have something with the same quality of our normal system, but actually we found that we are now doing better by this side effect of not having a spin-up. Now, what we want to do is to connect this part of the URDA with the observations we are receiving from Audi. And but for that, we have to do different things, many things. In particular, we have to have a proper observation operator for these observations. And this is not a simple task, because we are speaking of a moving weather station, which is going to be heavily influenced by the velocity of the car, by the color of the car, by the model, but whether it was in the garage or it was in the city or in a highway. So we have to come up with very sophisticated quality controls for that. And we have also to model the dependency of the meteorological state and what the model measures, which is very heavily influenced by the velocity. Yeah, something interesting here is that we have to do bias correction as it is done for aircraft. And that has to be done normally for car by car, which is a problem because privacy law protections, privacy protection laws, go against that. We cannot do this bias correction in DVD. We cannot know which car measured that. So it has to be done in a different way. It has to be done in the car. And afterwards, we have to come up with clever aggregation techniques, both in space and time, which of course give us a lot of room to play in order to respect data anonymization. So the references. Thank you very much.
Thank you.